Download this code from codegive.com, link in the description below. An in-depth explanation of code complexity, dev tutorial with code examples. Code complexity is a measure of how difficult it is to understand, maintain, and debug a piece of code. It's a crucial factor in software quality, impacting everything from development speed to software reliability. Managing code complexity effectively leads to better, more maintainable, and more robust software. This tutorial will delve into different types of code complexity, how to measure them, and provide practical examples in Python. Why is code complexity important? Maintainability. Complex code is harder to understand, modify, and fix bugs. This translates to longer development cycles and increased costs over the lifespan of a software project. Readability. Clear and concise code is easier for developers to understand, especially when working in teams or revisiting code after a long period. Reliability. Complex code is more prone to errors and unexpected behavior. Reducing complexity helps to improve the overall reliability of the software. Testability. Complex code is inherently harder to test comprehensively. Simplifying the code structure allows for more effective and targeted testing. Performance. While not always directly related, overly complex algorithms or data structures can negatively impact performance. Types of code complexity. There are several dimensions to code complexity. Here we'll cover the most important ones. 1. Cyclomatic complexity, McCabe's complexity. Measures the number of linearly independent paths through a function or method's control flow graph. Think of it as the number of decisions the code makes. Higher cyclomatic complexity indicates more complex logic and potentially more bugs. It's calculated using the formula, V, G, equals E, N plus 2, where V, G, is the cyclomatic complexity. E is the number of edges in the control flow graph. N is the number of nodes in the control flow graph. In simpler terms, it often correlates to the number of if, else, elif, for, while, case, break, continue, and goto statements, in languages where it applies, within a function. Each of these adds a branch to the execution path. 2. Cognitive complexity. Aims to measure how difficult it is for a human to understand the code, taking into account factors that make code harder to read and reason about. Considers nesting, control flow breaks, example break, continue, return, and operator precedence. Intended to be a more intuitive and human-centric metric than cyclomatic complexity. It emphasizes the mental effort required to grasp the code's intent. 3. Temporal complexity, time complexity. Describes how the runtime of an algorithm scales with the size of the input. Expressed using big O notation, O, N, O, log N, O, N caret 2, etc. Focuses on the dominant operation within the algorithm. 4. Spatial complexity, space complexity. Describes how the memory usage of an algorithm scales with the size of the input. Expressed using big O notation, O, N, O, 1, etc. 5. Code volume/lines of code, LOC. A simple but often relevant metric. Longer functions and classes tend to be harder to understand than shorter ones. However, LOC should not be the sole metric for complexity. Concise code can still be complex. 6. Nesting depth refers to the maximum level of nested control structures, example if statements within for loops within try blocks. Deeply nested code is harder to follow. Measuring code complexity, tools and techniques. Static analysis tools. These tools analyze source code without executing it. They can detect potential issues, including high cyclomatic complexity, duplicated code, and coding style violations. Examples include Flake 8 with McCabe plugin, Python calculates cyclomatic complexity. Radon, Python calculates cyclomatic complexity, Halstead metrics, and maintainability index. SonarCube. A comprehensive platform for code quality and security analysis that includes complexity measurement. PMD, Java offers a wide range of rules for detecting code smells and complexities in Java code. Check style, Java focuses on enforcing coding standards, including rules related to complexity. Code reviews. Having other developers review your code can help identify areas of complexity that you might have missed. A fresh perspective can often spot potential problems and suggest simplifications. Profiling, for temporal and spatial complexity, use profiling tools to measure the actual execution time and memory usage of your code with different input sizes. This helps identify performance bottlenecks and assess the temporal and spatial complexity empirically. Python C profile module is a good starting point. Manual inspection. Sometimes, the best way to understand the complexity of code is to carefully read it and try to understand the logic. Ask yourself questions like how many different execution paths are possible? How deeply nested are the control structures? How many variables need to be tracked to understand the function state? Code examples and reducing complexity, Python. Let's illustrate these concepts with Python examples and demonstrate techniques for reducing complexity. 1. High cyclomatic complexity example. This function has a high cyclomatic complexity because of the nested if statements. To reduce this, we can use several techniques. Decomposition. Break the function into smaller, more focused functions. Lookup tables, dictionaries. Replace conditional logic with a dictionary mapping. Here's the refactored code. By decomposing the original function into smaller, more manageable functions, process_data_type_A, process_data_type_B, process_data_type_C, and using a dictionary to map data types to their corresponding processing functions, we have significantly reduced the cyclomatic complexity of the main function, process_data_refactored. The code is now easier to understand, test, and maintain. Note how the process_data_concise version is even more condensed. 2. Nested loops, temporal complexity. This function has a time complexity of O, and (2), because of the nested loops. To improve this, we can use a hash table, set, to track scene elements. The optimized version has a time complexity of O, n, because the in operation on a set has an average time complexity of O, 1. 3. Long function, code volume and readability. This function is a classic example of why long functions are bad. It violates the single responsibility principle and makes the code difficult to understand and maintain. The solution is to break it down into smaller, well-defined functions, each responsible for a specific task. 4. Cognitive complexity example. The cognitive complexity is high because the nested if statements force the reader to keep multiple conditions in mind simultaneously. We can simplify this by using early returns and guard clauses. The refactored code is much easier to read and understand because each if statement effectively eliminates one possibility, making the remaining logic simpler. Best practices for reducing code complexity *. Asterisk keep functions short and focused. Asterisk adhere to the single responsibility principle. Aim for functions that do one thing well. Asterisk use meaningful names. Asterisk choose names for variables, functions, and classes that clearly describe their purpose. Asterisk write clear and concise comments. Asterisk explain the why behind the code, not just the what. Asterisk avoid deep nesting. Asterisk use techniques like early returns, guard clauses, and decomposition to reduce nesting depth. Asterisk use appropriate data structures and algorithms. Asterisk choose the data structure and algorithm that best suits the problem to optimize performance and reduce complexity. Asterisk refactor regularly. Asterisk don't let technical debt accumulate. Make time to refactor code and simplify complex areas. Asterisk test thoroughly. Asterisk write unit tests and integration tests to ensure that your code is working correctly and that changes don't introduce regressions. Asterisk use design patterns. Asterisk design patterns can help to structure code and reduce complexity by providing proven solutions to common problems. Asterisk prioritize readability. Asterisk write code for humans, not just for computers. Asterisk embrace immutability where appropriate. Asterisk immutability can make reasoning about code easier. Conclusion. Asterisk managing code complexity is an ongoing process. By understanding the different types of complexity and employing the techniques described in this tutorial, you can write code that is easier to understand, maintain, and test, ultimately leading to better software. Remember to use static analysis tools, conduct code reviews, and profile your code to identify and address complexity issues proactively. Regularly refactoring your code and adhering to best practices will ensure that your software remains maintainable and robust over time.